All right, good afternoon, everybody. Ooh, that was not bad. I got an excellent response in my left ear. Can we get the other half of the room this time? Good afternoon, everybody.
Good afternoon.
Oh, much better, much better. Okay, we've got some good stuff this week. And most exciting of which is it's the last major stuff. This is the final section, guys. That's it. And then the chapter is over. So next week is our assessment. And then the week after that, we get to play with some of the weird geometry topics, the like fourth dimensional crazy stuff. And then we've got our last project of the year, and that's it. We're almost done. So let's kick it off. Let's end this on a high note, okay? Let's do the best we can with this last section, because it is fundamentally one of the most significant, most practically useful possible topics. Volume. We live in a three-dimensional universe. Okay, physicists would argue fourth dimensional, time, space, but whatever, right? Spatially, 3 dimensions. Everything we interact with has 3 dimensions to it, so everything has volume. In fact, the past couple of sections we've dealt with area. That's been a lie. All of those application questions are technically false because everything has thickness, okay? Paper has a thickness to it, right? This is especially true when you start comparing really thin, like tissue paper, to the really thick, like construction paper, right? It's got a 3rd dimension to it. We just usually only... Am I supposed to be eating in here? Anyways, right? We usually only talk about the length and the width, right? 8.5 by 11 sheets of paper. But what happens when you take that paper and you start stacking it up? All of a sudden, what you thought of as, negligible, it's only a thickness of a piece of paper, barely worth mentioning. But you put 500 sheets of paper together, and now you got this great big thick ream, right? And it's heavy now, and everything. So it adds up. Volume is critical for almost everything we're dealing with. So since we've got a nice long week, we're going to break it up into 2 problem sets as we've done in the past. The first one today is mostly exercise. Just practice with the basic shapes. Okay? And then on Wednesday, we'll do more of the application. You get a teaser of that, though, at the end of level 1 here with the great pyramids of Giza. We can find out how much total stone is involved there. It's pretty cool. All right? And you, of course, can go beyond with the other levels as well. Okay. So I want to do a couple examples today. One, practicing just with that basic volume of a shape, and 2, dealing with a unit conversion in 3 dimensions. So if you haven't already, take out your notebook, follow along. Let's find the volume of this thing, whatever it is. In fact, that's honestly the first step, is to identify the thing, right? If you're already given the shape, your first step is to identify it. If you're not given the shape, your first step is to read the problem and figure out what the shape is, and then identify it, so that you can use the appropriate formula. Our textbook gave us lots of different formulas. If it's this shape, use this formula. If it's this shape, use that formula, right? They even summarized it for us in this table here. Right? Everybody has this table in their notes, yes? You better? No, you don't? Okay, well, your extra homework tonight is to go back and add this. All right? This is a hugely useful reference. Okay? In fact, whatever page this is on, I would star that page, up in the corner of the page so you can flip through your notebook and find it real quick, because this is really useful. Okay? Great shortcut. As soon as you know the shape, look at this table, right, circular, cylinder, or whatever it is, and you go across, here's the surface area, there's the volume, boom, I've got it. Right? You got your formula. Identify your shape, find your formula, and substitute in the measurements into the formula. That's the whole process. That's what we're going to do right now. So looking at this shape over here. Can anybody identify what shape that is? Out of you were busy drawing it. I'll give you another 30 seconds here. Alondra, what do you think? What kind of shape? Yeah. Don't know. Do you at least know what it's not? The process of elimination eliminates some things. There's no circles involved, right? Nothing about this appears round. Agreed? So that eliminates cylinders, that eliminates cones, that eliminates spheres, right? There's only two options left on our table. It's either a prism or a pyramid. Yeah? Okay, Alondra, does everything seem to come all to one point? Like a pyramid? Yeah? There is one point that, like, this reminds me of that thing in Egypt. No, does not remind us of the thing in Egypt. Not a pyramid. Those Egyptians, guys, were really useful for geometry shapes, right? Great reference point. So it must be some kind of a prism. If that were true, then we could identify two identical, that is to say, congruent shapes that are connected by a series of rectangles. Is that true? You guys see that? Now, this is a perspective drawing. Well, actually, no, it's not a perspective drawing, but it is a 2D drawing of a three-dimensional shape. So when I say connected by rectangles, those rectangles may look like parallelograms. That's the reality. That's how you get it to fit on a flat surface. So this is a trapezoidal prism. Okay? Here is one trapezoid. They've shaded it in for us. Okay? That's the part sitting on the table. There's an identical trapezoid right above that. Right? And then each point is connected, right, with a straight segment, which means there's a rectangle here, there's a rectangle here. It looks like a parallelogram because you have to visualize this in three-dimensional space. That's a rectangle reaching back into the page. Right? This rectangle here, this little skinny one, is behind. That's in the back. And this great big one is in front, right up in our face. And then we have these trapezoids are the top and the bottom. Does anybody not see that? Speak now, because that's what we'll have to work. If you cannot visualize that, everything else is going to be way harder. Okay. So can we agree? Trapezoidal prism. Yes? Excellent. So we just need the formula for volume of a prism, which says, in general, take the area of the base and multiply by a height. I'm going to use a capital H this time. Height gets used a lot. And the base, as I said, is always the two matching ones. So in this case, it's the trapezoids. So our B is the area of a trapezoid. Why can't I draw another straight line? Yeah, there we go. So now we need to turn back and find our area formulas. Those should also be somewhere in your notes. Can anyone tell me the area of a trapezoid? What's the formula there? Go ahead and look it up. That's okay. What's that? Like that? Okay, 1/2 h times b1 plus b2. So our trapezoid has two bases. Base 1 plus base 2, a height, and we take half that. If you like this format, great, go for it. It is a perfectly valid format. I, however, have a personal preference. This is all multiplication. It's commutative. So I like putting the 1/2 over here as the bases divided by 2. Because then to me, it's more representative of average of the bases. Right? Add them both up and divide by 2, give me the average. So I take average of the bases, multiply by the height. That's just conceptually how I like to think of it. That's how I remember the formula. And so that's the way I usually write it. All right, now we just need to fill it in, substitute in. What is the height of our trapezoid? Of the trapezoid. Not the height of the whole thing. That's why I went ahead and called this big H, to distinguish it from little h. So just the trapezoid. Just focus in on this shaded guy. It looks like 4, right? This 4 is perpendicular to this 8. So it's like, hey, I remember Mr. Apple said, when finding the area, you always multiply perpendicular lengths. So the fact that they give us that right angle is a huge clue. These numbers get multiplied together. So we'll call 4 is the height. One of the bases is 8. It's right there. What's the other base? It's what? It's 2. You sure? Like it should be right here, right? The 2 bases, parallel sides of the trapezoid. But they don't give us a measurement there. But this trapezoid is perfectly identical, congruent to this one. So all of these measurements I can transfer down. This is 2, this is 5, this is 5, right? The only one I actually need is 2. So that other base is 2. And now the area of that trapezoid is, oh, we can do this one together easy, right? Start from the inside out. No, put the calculator down. Everybody, 8 plus 2 is, 10 divided by 2 is, 5 times 4 is 20. 20 what's? Centimeters squared, very good. Right, that was an area, so units to the power 2. We're almost done. We have our base. We have the size of our sheet of paper. And now we need to stack up duplicates of that sheet of paper up and up and up, layer by layer, until we are 10 centimeters tall, right? So back to volume is now the 20 centimeters squared. That's our capital B area of our base, times the big height of the whole thing, 10 centimeters. For a grand total of 200 what? Centimeters cubed. We are in 3 dimensions. Volume is the 3D measurement, so my power of the unit is 3. And we can also track back. If I had written down my centimeters every time, we'd have figured out I multiplied centimeters 3 times in total. Okay, any questions on volume of I'll call them a basic shape, just one shape off of that list of formulas. Clearly, we could get more complicated with like connecting 2 shapes to each other. If you do like the ice cream cone plus the ice cream, it's a cone plus half a dome on top thing. A compound shape there. No questions here? So I could give you any shape from that list. And you could just take the measurements, find the volume. No problems? Nothing that stands out to you, at least? You'll find the problems when you get there, right? Okay. Good. Again, the hardest part is identifying the shape. Once you know the shape, the volume formula is set. The measurements are set. The You might have to find some measurements like we did with that other base. Right? In a problem context, right, a word problem presented to you, that might be the most difficult part, is figuring out, well, they're just describing the thing that's going on here. You might need to draw a diagram or two to figure out what actual shape are they describing. Where do each of the measurements go? They tell me the length of this arm is half the length of that robot arm, and this part is twice that, right? Work out what they're talking about. But then once you have the shape and have the measurements, look up the formula, substitute it and go. Okay? The next tricky bit, the other thing that a problem scenario might give you trouble with, is the units themselves. And so we're going to practice some three-dimensional unit conversion. Okay? I have here a can of juice. I've been eyeing this thing at the grocery store. I'm like, that seems like a decent-sized can. I wonder how much actual juice is in there. I want to know how many cups worth of juice, because I have a cup of juice every morning. I'd be like, is this a month's supply of juice? How many days can I drink a glass of juice each morning out of this can? That seems like a fairly practical thing to want to know, right? Especially if you're grocery shopping. You're trying to figure out, okay, do I buy this one? Do I get the big can? It costs more, but maybe it's cheaper per ounce. These kinds of price comparisons. However, any measuring tool you bring with you to the grocery store to measure said cans, right? I measured them in centimeters. They won't let me open the can of juice there at the store. They frown upon that. So I had to measure the outside. This is what I got. I don't drink my juice in cubic centimeters. Right? I don't know about you guys, but I open the cupboard and I take out a cup, not a cubic centimeter. Maybe you're different. I don't know. Engines are measured in cubic centimeters. Okay? Juice glasses are measured in cups. So I want to find the volume and convert it to cups. Okay. Step one of any volume problem, identify the shape involved. What shape are we dealing with here? A cylinder. Yeah, it's a can, right? We're also given a radius. Anytime you're given r equals, oh, that's a radius. R always stands for radius. And I can't think of it. Yeah, R is one of those unique letters that only gets used for basically one thing, radius, every time. So a circle is involved somewhere. It's got to be one of those round shapes. Yeah, and we know juice cans from real life. They look like cylinders, so we've got a radius R and a height h. Okay, volume of a cylinder is AH? Okay, but what is the area? Give me yeah, pi r squared h. AH is the general one that worked for the other prisms as well. Cylinder is specific enough, I would just go straight to pi r squared h. This is typically how they'll present it. They'll give you the radius. All right, let's substitute some things in. Pi is always pi. My radius here they give me is 5.3 centimeters. Square that, multiply by h, 17.7. So I get, let's keep it in terms of pi first. Do one step at a time. So if you would all please square 5.3 and multiply by 17.7. Give me that number first. And let's see, these numbers are given to one decimal place. So that's probably as accurate as I want my final answer to be. So let's maintain one more decimal place while we're in the middle ground. So go to 2 decimal places. And then we can round our final answer to 1 decimal place. Does that make sense? Go one more. Don't want to risk losing too much accuracy there. You look like you have a number. What do you got? pi. Okay, can we get a confirmation on that? Anybody second this number? I see a head nodding. Okay, good. All right, and that'll be in a volume, so it should be centimeters cubed. Now, I know in the past I've said, hey, keep that pi for as long as possible, but we're clearly not going to leave our final answer in terms of pi. I do not have my juice glasses marked in increments of pi's. I guess I could do that. That would be a pretty nerdy thing to do. But I'm going to get a decimal approximation anyways. Spoiler alert, unit conversion is all multiplication. So the order here doesn't really matter. Let's go ahead and multiply by our pi, and we'll stick to 2 decimal places. So plug your pi in and give me that to 2 decimals. Say that's almost 500 times a little more than 3. So 1,500, 1,600 maybe? Okay, whoever has a number, shout it out. Yeah. What was the last bit? 9.6, thank you. Centimeters cubed. Confirmation? Yes? 0.97? 9.6. Yeah, that should round up to 7. Okay. There we go. So that's the volume, again, in cubic centimeters. Now comes the fun part, the unit conversion. So every unit conversion, turn it into a fraction. Set the whole thing over 1. And now we're going to multiply by more fractions. It's okay, all of these fractions are actually versions of 1, right? Because we're going to turn these unit equivalences into fractions. Right? We're going to set one over the other. So I need to convert from cubic centimeters to cups. Now, you could ask Google, hey Google, let's convert cubic centimeters straight to cups. And it would do all the computation, the middleman stuff for you, and give you that direct result. However, you won't always have access to that, right? Certainly not on a test. But we do have access usually to much more standard unit conversions. For instance, I know a cup is 8 ounces. Okay? Metric system has defined a cubic centimeter is 1 milliliter. Okay? That's very handy. That's a very convenient conversion. And it's also pretty standard to go from ounces to milliliters. 1 ounce is worth 29.57 milliliters. So these are standard conversions, and we can combine those together to get the one we want. Okay? These you can probably look up. You might have in some table somewhere, maybe on the back of your planner or attached to your calculator or something, right? Or given to you on some test. So let's practice using them. Even though, yes, again, you could look up a specific one each time. So I have centimeters cubed. The only one I can convert to right now is milliliters, so let's start with that one. Since I have centimeters cubed, I want to get rid of it. We're going to put centimeters cubed in the bottom, and milliliters goes on top, and then put the numbers with each unit. In this case, it's 1 and 1. And now, centimeters cubed is on the top and the bottom, which means I can cross them out. They will cancel out or reduce. And the only thing left is milliliters, right? I have now successfully converted to milliliters. Well, okay, it was metric. It multiplied by 1 over 1. It didn't actually change anything. Now, I would like to stop here and point out, because we're going to milliliters, we actually have a fairly convenient shortcut on our hands, because humans have decided that we do so much with volume that it's worth having specific volume units, such as cups and ounces and milliliters. Okay. And so I can convert directly from a cubic linear unit straight to the volume unit. Let's say hypothetically, instead, we wanted to know, hey, cubic centimeters is great, what about cubic inches? Okay. Or you measured your flower bed in cubic centimeters, you go to Home Depot, you buy mulch in cubic yards, right? Well, those are all cubic versions of linear measurements, which means if you were to convert, say, and just pick a number, 5 centimeters cubed. If you wanted to convert that to inches, we have a conversion for centimeters to inches. It's 1 inch is 2.54 centimeters, but the number doesn't matter here. What I want you to notice is the difference in power. We started with centimeters cubed, but my conversion factor is inch to centimeter single. I can't use this by itself. I need to match all 3 powers of centimeters, which means I need to use this conversion 3 times. Right? Centimeters cubed, centimeter, centimeter, centimeter. Power of 3. Now, some people like to group those together and just go ahead and, multiply that and do, okay, inch cubed to centimeter cubed. And you can do that all in one if you wanted to, right? And then I have cubed cancels with cubed, or 3 independently. Works either way. So this example doesn't have us do that, but there might be one, either in this problem set or the next one, that will ask you to do such a thing. Okay? It will keep a cubic linear measurement. Questions on that? A little diversion there. All right, back to the problem at hand. I now have milliliters. That is a standalone volume unit. I don't have to worry about triplicating the conversion. But I don't want milliliters. I want cups. Well, cups can be broken into ounces, and ounces has a certain number of milliliters. So now we can convert milliliters into ounces. Let's do that now. Multiply by another fraction. I have milliliters. I want to get rid of it. Stick them on the bottom. Convert them to ounces. Put that up top. Put the appropriate number with the appropriate unit. So however this was given to you, whatever was equal, 1 goes with ounces, and 29.57 goes with milliliters. So 1 goes up top, 29.57 goes on bottom. And now I've got milliliters on top, milliliters on the bottom. I can cross those out. The only unit left is ounces. I don't want ounces. I wanted cups, so we got to go one more time. Ounces on the bottom, cups up top. 1 cup contains 8 ounces. I can now cross out ounces. The only unit left is cups. That's what I wanted. Ding. No more conversions to apply. Now I can perform the calculation. Multiply straight across. We're just going to take this number, multiply by everything in the numerators. In this case, it's 1 times 1 times 1. Okay, so you can ignore any 1s, because multiplying by 1 doesn't change the number. and then divide by everything in the denominator. In this case, we got a couple ones to ignore. We got two numbers here. So final computation is just 1561.97 divided by 29.57, divide again by 8. Please round that to 1 decimal place. She says 6.6. Yes? Confirmed, 6.6 cups. Final answer. So if I have a cup of juice every morning, how long is this can going to last me? 6.6 days. So a week, right? It gets the weekdays in there. That's the most important bit, you know. Maybe on Saturday, I can have I have to decide, what do I do with that 0.6 of a cup? Do I have like a 1.6 extra big cup at the end? Or do I save the 0.6 for day 7 and have just a little bit? A personal decision you got to make there, but there we go. Can a week. Questions on 3D unit conversion? Any other questions in general? Yes. All right, then I will leave you guys with the rest of the time to start the problem set. And let's see, how many we got here? 2, 4, 6, 8, 10. Even number, perfect. Pair up, work together. Okay, take advantage of your time here. Do I have a spare mask? Yeah. I do not, but the nurses probably do if you want to head for them. Just go after class? Okay. Yeah. Well, then school will be over. Oh, okay, for that, yeah. All right.